inverse Z transform, there are three main methods that are covered in the book. Inverse Z transform. We will cover all the three methods. The first method is called by inspection. Okay, it's called inspection method or using the Z transform pairs. The second one is partial fraction expansion. Partial fraction expansion method. It's called PFE. And the third method is called the power series method. Power series method. Okay, we're going to be covering all of that. However, there is a fourth method which is present in many DSP books and in the study, and this is called the inverse Z transform via contour integration. Contour integration. Contour integration is a technique that is used in complex variable theory and requires us to get into the properties and behavior of contour integration and then show that the Z transform has got a explicit inverse with respect to the contour integral. What we will do is we will just mention what is the Z transform. We are not going to get into the contour integration steps. However, if you are interested, definitely we can point you to certain textbooks which will give you those. But the most important thing is that we have three methods by which we can do the inverse Z transform, and that is good, more than adequate for the discussion that we are going to be looking at. Okay, so the first of the methods is called the inspection method. Inspection method basically says, let us look at the Z transform table and or the Z transform pairs and see how to get the inverse Z transform. Inspection method. Okay, so basically look at Z transform pairs and Z transform properties. Basically, we're going to use a combination of these two tables to get the result that that we are interested in. So, for example, very more or less sort of a trivial example. Okay, 1 over 1 minus AZ inverse. If this is given to us, then we say that we can write it as and mod Z greater than A is less than 1, A is greater than 0, less than 1. Supposing this is given to us, the inverse Z transform is very easy for us to write down. H1 of n is equal to A power n U of n. Why? Because we know the Z transform pair A power n U of n has got this Z transform, so therefore we are quite familiar with this. Now, take it a little bit in the same method, same way, but something not as obvious in terms of the answer. Okay, 0.5 Z divided by Z squared minus Z minus 0.25. We are given that mod Z is greater than 0.5 is the ROC. Okay, so let us see if we can simplify this. Always, our Z transforms, particularly if you want a causal sequence, is better to have it in terms of Z inverse. So this term can be rewritten as in terms of powers of Z inverse. So this will be 1 minus Z inverse minus 0.25 Z power minus 2. And the numerator will be 0.5 Z inverse. What did I do? I pulled out Z power Z squared, and then you will get the following expression, and then take this Z squared to the numerator, you will get the corresponding expression. So now if you look at the denominator can be simplified or rewritten as 0.5 Z inverse divided by 1 minus 0.5 Z inverse the whole squared. Okay, and this is a form that we are familiar with, and this is a form that we can always use and exploit. And this basically says that, go back to the Z transform pair, where it says that n times a power n u of n has got a Z transform which is given by a Z inverse divided by 1 minus a Z inverse the whole squared and mod Z greater than a. Okay, this is the relationship. So from this we can then say that H2 of n has got a value that we can now write down as n times 0.5, I am writing it as half raised to the power n u of n. Okay, so again, I hope you are starting to see the approach. You get it into a form that is already known to us, and then we use the table to relate it to the form that we are interested in. Okay, so that is primarily the way by which we exploit the inspection method. Okay, now remember I also said that we can use the properties of the Z transform, and so here is an example of utilizing the property of the Z transform. Okay, and another example, x of Z is equal to 1 over Z minus 1 by 4 mod Z greater than 1 by 4. Okay, so obtain x of n. This is the statement of the inverse Z transform problem. Again, we are going to use the following method where we write it in terms of Z inverse. This becomes Z inverse divided by 1 minus 1/4 Z inverse, and we can do it in two methods. Method 1, the numerator is a Z inverse, that means it is a time shifted sequence. So we use the result that 1 minus 1 by 4 Z inverse corresponds to a sequence which is 1 by 4 raised to the power n u of n, okay, where ROC is given as mod Z greater than 1 by 4. Okay, and if I needed to have Z inverse 1 minus 1 by 4 Z inverse, that means it is a sequence that is delayed in time, shifted or delayed. You can then say that this corresponds to, which way are we going? Z inverse is a delay, so therefore it will be 1 and delay of 1 unit. So therefore this will be 1 by 4 n minus 1 u of n minus 1. Okay, what property did we use? The property of the time shift property. Okay, this is using the time shift property. Okay, now of course we can do it in one more method. Let me just highlight that method for you, and this goes back to some terminology. When you have a ratio of polynomials, a rational form, okay, so if you, let us say, have h of z equal to n of z by d of z, n of z is the numerator polynomial. In basically it's a function of z, so therefore powers of z inverse will be there. Polynomial, we will say that the order is equal to m. Okay, it's a polynomial of order m. D of z is the denominator polynomial of order n. Polynomial of order n. Okay, you have a ratio of two polynomials. For the numerator is order m, denominator is order n. If m is strictly less than n, this is called proper rational form. numerator is less than the order of the denominator, proper rational form. Okay, m greater than or equal to n, this is called an improper rational form. Okay. So first test, is this expression z inverse by 1 minus 1/4 z inverse, is it a proper rational form or an improper rational form? Obviously this is an improper rational form. Numerator is order 1 and denominator is order 1, so therefore improper rational form. Okay. Now it is also known that in algebra, whenever you have an improper rational form, you can convert it into a proper rational form. So that's rational form. How do we do that? And typically it is by dividing. The numerator polynomial is larger than the denominator polynomial, so therefore you can convert it in terms of the form. So let me just sort of give you an example. Okay, supposing you have a Z transform which is given by 1 plus 3 Z inverse plus 11 by 6 Z minus 2 plus 1 by 3 Z minus 3 divided by 1 plus 5 by 6 Z inverse plus 1 by 6 Z minus 2. Okay. Typically what we do is you can do a long division, polynomial division, where you write the this term in the increasing powers of z. So z minus 3, z minus 2, so basically increasing. So 1 by 3 z power minus 3 plus 11 by 6 z power minus 2 plus 3 z inverse plus 1, and this also you write it in increasing powers of z. So 1 by 6 z power minus 2 plus 5 by 6 z inverse plus 1, and then you go through the division. What you will find is that you will get 2 times z inverse plus 1, and then you will have a remainder. It doesn't divide perfectly. The remainder is 1 by 6 z inverse. So what we are saying is this improper rational form can be written as 2 times z inverse plus 1 plus 1 by 6 z inverse divided by the denominator. Okay, so basically this is in a proper rational form. This is a proper rational form. Okay, so what have we done? We took the improper form and then took out a factor, basically the quotient, and then what was left over we wrote it as a proper rational form. Okay, now what I would like you to do is convert this transfer function that we have, x of z equal to z inverse divided by 1 minus 1/4 z inverse, into a proper rational form. Okay, you can do it in multiple ways, but one of the ways, whenever you have only a first order factor, it is easy to do it in the following manner. Okay, let's write the numerator as minus 4 into minus 1 by 4 z inverse divided by 1 minus 1/4 z inverse. Okay, so basically I multiplied by minus 4 and minus 1 by 4. They will cancel out and giving you the same. This next step is minus 4 minus 1 by 4 z inverse plus 1 minus 1. That also will cancel, so therefore you will get the same expression. Okay, divided by 1 minus 1 by 4 z inverse. Now I am going to take the first two terms together and the last term together. So what does it come out to be? Minus 4 1 minus 1 by 4 Z inverse, the first two terms, divided by 1 minus 1 by 4 Z inverse. Okay, so obviously these two will cancel. So if you had done the long division also, you would have gotten the same answer, and what you are left with in the proper rational form will be equal to plus 4 divided by 1 minus 1/4 Z inverse. Okay, and so what we are saying is this sequence is equal to minus 4 plus 4 divided by 1 minus 1/4 Z inverse. How do I calculate the inverse Z transform? If this is x of z, okay, what is the corresponding x of n? The corresponding x of n for this will be minus 4 delta of n. Right? Minus 4 in the Z transform domain will give you minus 4 delta of n. And this one will be a scale factor of 1 by 4 multiplied by 1 by 4 raised to the power n u of n. Okay, so this is the second way that we have obtained. So notice that we have obtained the Z transform, the inverse Z transform in two ways. The first one was, directly using the time shift property. The second one is converting it into a proper rational form and then computing the inverse, again using the properties that we know from the. So now you may wonder that, are these two the same, the two expressions? Since you had the same x of z, same ROC, they have to be the same, the two x of n. So maybe it's a good idea for you to verify that the expression that we got from method 1 and method 2 are the same. So let me give that as a task. Verify x of n from method 1 or via method 1. Via method 1 is identically the same as x of n via method 2. All right. So we have started to look at the use of these properties, just so that we can get a good understanding of the inverse Z transform process. Now this is by inspection. Basically, you reduce it to a form for which you know the inverse Z transform.